In this installment, we're going to look at the coefficients of friction. So let's unpacking the table. We have 3 columns: system. We can see those are like the materials. We have the coefficients of static friction and the coefficients of kinetic friction. Notice that they use the word kinetic. And again, we want to shy away from using the word kinetic. We would rather use the words dynamic, or better as a descriptor, sliding friction. But kinetic leads to confusion. So let's look at our system. We'll look at the different materials we have. Rubber on dry and wet concrete. And we notice the difference. Oh, the coefficient is higher. So there's more friction when it's dry than when it's wet. And that's probably not surprising. Wood on wood, steel on steel, Teflon, shoes on ice, ice on ice. So the first thing to notice is that they're always pairs of materials, because there's a unique pairing between 2 surfaces always. It takes 2 to tango. It takes 2 different materials, 2 different surfaces for there to be friction. And each of them has different properties. And it may be that some materials like ice we know are slippery no matter what it is, because it has a very, very, very smooth surface. It's also slippery for a different reason, and that different reason is that it does not take very much pressure on ice for it to liquefy. So you have ice on top, ice, and then there's liquid water on top, and that's how, like, ice skaters, how that works. Ice skaters with their blades, they push on the ice. That pressure causes the solid ice to become liquid, and so it's easier, as we'll see a little bit later, for things to slide when they are liquid. So in any case, we have a bunch of pairs of materials and various pairings. Then when we look at the static friction values themselves, some observations are, let's see, our largest value seems to be so far is 1. And let's look for our lowest and smallest, 0.14, 0.05, 0.04, 0.016. So that looks like our smallest value. And so our observation are that mu s ranges between 0.016, and that is less than or equal to mu static, which is less than or equal to 1. So that's, now we're not saying that there may not be some that are higher, but at least in this table, those are the range of values we have. And we notice that when it's wet, we tend to have lower friction. When we go to the dynamic or the sliding friction, we look and we can see that the largest so far seems to be 0.7, 0.1, 0.03, 0.04, 0.015, 0.03, 0.02. So the observations here might be that we have 0.015 is less than or equal to mu dynamic, which is less than or equal to 0.7. So that's another observation we might make. Another observation, so now, so we make those observations. So observations, when we look across the aisle, we see in every case the dynamic is lower than the static. So that's a pattern that mu d is always less than mu s. Or we could say the opposite of that, which is mu s is always more than mu d. If we notice the rubber in concrete tends to have high values. Wherever we have ice, we have low values. So these are the values. Ice, low values. And we have concrete, and rubber is high values. So those are just some patterns and trends to recognize. But I would say the biggest takeaway here is that the static is always larger than the dynamic. And so far what we've seen is that there are no values larger than 1. Well, let's explore that a little further. That there don't seem to be any values larger than 1. And we'll explore that. Let me just add that. There appear to be no values larger than 1. Greater than 1. And we will see why that is in subsequent installments.